We've previously been looking at how you can use differentiation to find the stationary points on a curve. So let's just look at an example of what we were doing then. Suppose we have a curve y equals x cubed, subtract 6x squared, subtract 15x plus 1. We know how to differentiate this curve. We know how to work out dy dx, the gradient of the curve at any point. That is 3x squared, subtract 12x, subtract 15. And we know that the points where this curve has maximum or minimum points are the points where dy dx is 0, where this gradient is 0. So to find those points we have to solve, in this case, where is 3x squared, subtract 12x, subtract 15, where is that equal to 0? Well, if we're going to solve this, the first thing we could do would be to divide everything through by 3. That will just make the numbers easier for us. And if we are lucky, this is going to factorise. It does in this case. So it's going to be x plus or minus something times x plus or minus something equals 0. And it doesn't take a lot of thought to realise that that's a -5 and a +1. So if the product of those two brackets is 0, it can only be because one or the other bracket is 0. So either x subtract 5 is 0, in which case x is 5, or because x plus 1 is 0, in which case x is -1. And if we want to find out the actual y values that go with these x values, that's a bit better, we can plug the 5 back into the equation we've got at the top. If we did that, we would get a y of -99. That's a bit tedious to do here, so you can either take my word for it or verify it for yourself, but if you check it out, I'm sure that's what you will find. If we throw in an x value of -1, we'll get a y value of 9. So therefore the coordinates 5, -99 and -1, 9 are the stationary points on the curve. So we now have to identify which are the maximum and which is the minimum point. This isn't a tremendously sophisticated curve. You may have other ways that you can tell just by looking at them which one is going to be which, but we're going to investigate a method which you can use in more complicated situations where it may not be at all obvious. So the first thing we have to do is introduce this concept called the second derivative. What do we mean by the second derivative? What we mean is take the first derivative, take dy dx, and differentiate that. So we're effectively differentiating the curve for a second time. So if we differentiate dy dx, the notation for this is d2y dx squared. That's just the way that we write this in one go, because you can see we're doing d to dy. It's like we've differentiated y twice, and on the bottom we've got a dx and another dx. It looks a bit like dx squared. But don't worry about the notation. You just have to remember that d2y dx squared is the notation we use for the second derivative. So what's that going to be in this case? Well, we've already worked out that dy dx is 3x squared, subtract 12x, subtract 15. So to find this second derivative, we just have to differentiate that. That will give us 6x, subtract 12. Now that we've done this, what good is it to us? Well, what you have to do is put the different x values for the stationary points into this expression, and depending on what we get, we can tell whether the points are maximum or minimum. The general rule, I'll go on at the end of this video to describe why the rules work like this, but for the general rule, if you just want to know what it is that if the second derivative is positive, then that means that the point is a minima point, a minimum. And if the second derivative is negative, that means that our point is a maximum. If it turns out that the second derivative is 0, then we can't conclude anything. We don't know. We'll have to investigate what kind of stationary point we've got using other methods. So let's see what happens in this case. In this case we've got our second derivative of 6x subtract 12. If we put in the first x value, the x value of 5 from the first stationary point, then that means that d2y dx squared, since we know it's 6x subtract 12, 6x, 6 times 5 is 30, subtract 12, well, that's going to give us 18. But I'm not really so interested in the value itself. What I'm interested in is that this is greater than 0. Therefore, this point is a minimum. And if we put in the x coordinate of the other stationary point, x equal to 1, then now we have that the second derivative is 6 times 1, 6, subtract 12 is negative 6, and again I don't really care so much about the value. What I care is that it's less than 0, so this point is a maximum point. So take your curve, differentiate it once and put that equal to 0 to find where your stationary points are, then do a second derivative and check out whether it's positive or negative to find out whether your points are minimum or maximum points. I said I'd have a little chat about why this method works. So let's think about it like this. If you've got a set of coordinate axes, if you've got a curve, let's think about a curve which has a minimum point like this. We've already just talked about how the gradient of this curve, which is what dy dx means, is what enables us to find this point, because at that point the gradient will be 0. That line will be horizontal. But think about the gradient just either side of it. As we're getting closer to that point, we've got a negative gradient. As we go the other side of that point, we've got a positive gradient. In other words, as we do this journey through the point, the gradient is getting bigger. Here it's negative, then it's 0, then it's positive. Well, one way to think about what a derivative means, or what a gradient means in general, is it tells you how one thing changes with respect to another. When we're working out dy dx, what we're saying is how does y change with respect to x. For example, if you've got a gradient of 0, y doesn't change with respect to x. So the change in y is 0. The gradient there being 0, that's why the derivative tells you about that. At this point here where we've got a positive gradient, that means that as x changes, y changes in a positive way, and the value of the gradient will tell you exactly how much y changes with respect to x at that point, and so on. Well, that means therefore that the second derivative, d2y dx squared, tells you how the first derivative, dy dx, changes. So if it's positive, if the second derivative is positive, that means that the first derivative, dy dx, is increasing. It's getting bigger, and that's what happens when you go under a minimum point. The gradient is getting bigger. Starts off negative, then it's 0, then it's positive. And similarly, if you had a second derivative which was less than 0, that must mean that the first derivative, dy dx itself, is decreasing. So in a sketch we might have some point like this, where when you're at the top of the curve the gradient is level, is 0, that's meant to touch the point there, but beforehand it's a positive gradient, afterwards it's a negative gradient. In other words, the gradient itself is getting smaller, the gradient is decreasing. That's why a second derivative which is less than 0 identifies for you a maximum point.